Yeah, hello and welcome to the Scanning Microwave Microscopy webinar from Nanosurf. So we will wait a few more minutes because I see that some attendees are dropping in, so 1 or 2 minutes, and then we're going to start with the webinar. So just stay put for the moment. Okay, I see we get more and more people here dropping in. That's good. So not starting immediately on time was a good idea. So, but also to the newcomers, we'll start shortly. No worries. Yeah, good. More and more people. Let's see how the flow will stop. And then we can give the presentation to the most people. Okay, I think now should be fine. So yeah, also hello and welcome to the newcomers to this Scanning Microwave Microscopy webinar from Nanosurf. My name is Gotthold Fleschner and I will be your host for this session. Our today's speaker, Denis Vasyukov, has quite a broad expertise that he was able to collect in several renowned institutions in Russia, in Israel, in Singapore, and in Switzerland. He worked in magneto-optical transport as well as in the development of nanosquids, but most importantly for us today in this webinar, he has extensive experience in developing and using microwave scanning probe microscopes, as he did, for instance, in the Swiss Federal Institute of Metrology, as well as here at Nanosurf. So the idea of this webinar will be the following. For your convenience and for the safe execution of that webinar, Denis has recorded his talk and I will play it for you in a moment. During and after the talk, you can use the chat box to ask questions, which Denis will answer then later after the talk. All right, so that would be it. So without further ado, let's roll the clip. Just a moment. And here we should go. So enjoy.
Hello everyone, and welcome to the webinar. My name is Denis Vasyukov, and I'm an application scientist at Nanosurf. Today I will be presenting the Scanning Microwave Microscopy technique, or SMM. I will tell you what it is, how it works, and what is this technique useful for. I will also show you some application examples and ways to get quantitative data from your SMM measurements. So the first idea of scanning microwave was realized almost 40 years ago, but at that time it was not really a scanning probe method. It used free space microwave optics instead of cantilevers to deliver the microwave to the sample and measure their reflection. But already then, the signal that they measured was the reflection coefficient of these waves. And as you may expect from this free space optics, the lateral resolution of such a method was severely limited by the wavelength. But these researchers have managed to push it to the sub-wavelength resolution by introducing this small aperture through which the waves were released onto the sample. The modern SMM is not using free space anymore, because in free space the microwave signal is rapidly losing its power, and I will say a few words about it later. So instead of the free space, now we're using transmission lines, which are the low-loss coaxial cables. And the reflected microwave signal is collected in the near field or evanescent wave regime. A basic SMM setup would look something like this. You have a microwave source and a receiver, which are usually working on the same port. There are also two port configurations where you can split the forward and the reflected wave, and this could come in handy if you would like to measure the transmission rather than reflection. But the standard configuration is one port. Then the wave travels down through the impedance match, because the source has usually 50 ohm impedance and the tip sample contact has much higher impedance. And these two have to be interfaced somehow. And I will talk about it a bit more a few slides later. And then the wave enters the probe, goes down to the tip, gets reflected back, and travels the same path back to the receiver. So there it is registered, and the reflection coefficient is calculated by comparing the amplitude of the received and the transmitted waves. Now, what kind of information can we get about the sample by doing this measurement? SMM is an electrical mode. The microwave properties of the sample depend on the dielectric constant of the material and its conductivity. And these two quantities are essential for the development of the electronic devices, mostly semiconductor materials, where this method really shines, providing strong contrast between the different materials and the areas of different dopant densities. Another very useful feature of this method is that unlike most of the scanning probe techniques, we get information from the surface. The microwave is penetrated inside of the material for the distance that is called skin depth, and therefore the information is collected from the volume below the surface, allowing for the subsurface imaging. On the previous slide, I spoke about measuring the material parameters, which is the ultimate goal of the measurement. Now let's take a step back and get a little better understanding of the instrumentation. On the instrument level, what the electronics is really measuring is the tip sample impedance. In that sense, one might call it a microwave impedance microscopy. And the impedance is essentially a combination of the capacitance and the resistance between the tip and the sample. And it is through the measurement of these two we can extract the electrical properties of the sample. But this extraction depends a lot on the model of the sample and the tip itself, and often even on their surroundings. And while simple models work with simple samples, things quickly get complicated, and then often the way out is only to calibrate the measurement. Now I would like to introduce you a bit more to the terminology of microwaves and say a few words about the reflection coefficient, which we will be mentioning a lot today. So the reflection coefficient is called an S11 parameter. In a two-port system, there are four S parameters that define the properties of the device under test: S11, S12, S21, and S22. In the S11 case, the first one and the second one mean that the source wave and the received wave are generated and measured at the same port. So as I said, by definition, S11 is the reflection parameter. It is introduced as the ratio between the difference in the sum of the impedances of the source and the load. The impedance is a complex number, and therefore the S parameter is also a complex number. It has its imaginary and the real part, or in another interpretation, it has an amplitude and the phase. With the source impedance is usually 50 ohm and only has a real part, and the load impedance is a complex number, and its real part is the resistance, and the imaginary part is the inverse capacitance times frequency. And again, depending on the convention, instead of the impedance, one might work with microwave admittance. Then the real part is the inverse resistance or conductance, and the imaginary part is the capacitance times frequency. From the measurement of the resistance or conductance, you get the material conductivity, and from the capacitance, you get the dielectric constant. Now let's continue a bit more with the formulas and try to analyze them a bit. One consequence of the impedance being a function of frequency is that the changes in the S11 parameter, while changing the capacitance, are also frequency dependent. The higher the operating frequency is, the higher is the change in S11, and therefore the smaller is the smallest detectable change in the capacitance. In the microwave world, going to the higher frequency ranges is expensive and requires significant changes in the electronics. but within a given technology that defines the range, it is always best to go for the highest possible frequency. We have talked about the formalism and the terminology. Now let's move slowly to the more practical questions. We already know that the tip sample contact, because of its high impedance, is the natural reflection point for the microwaves. In practice, in your system, there would be other reflection points. For example, a bias T, which you would use to apply a DC bias to the tip. And you can also introduce some interferometer-like impedance matching elements in your transmission line to suppress the signals which are not coming from the tip. As the result, your transmission line will have many resonant frequencies, which are essentially defined by the system geometry. And the dependence of the S11 versus frequency will have these maxima and minima. And it turns out the useful signal from the sample is best when you work in the minima of the reflection. This is where the S11 has its highest sensitivity to the changes in the sample parameters. To find these minima, you have to be able to sweep the frequency. So it is very useful to have a system with variable frequency. Another application of variable frequency, and we'll talk about it later, is that you could access your sample on a different depth. Now let us look into the simplest application of the SMM, the determination of the dielectric constant of the material. Those who do this with the electrostatic force microscopy would recognize this formula. The physics is the same here, but the way of the measuring of the capacitance is different. The way you do this experiment is that you have a conducting substrate with a dielectric film on top of it, and you have a conducting tip above it. And you consider this system to be a parallel plate capacitor. Then if you know the thickness of the film and you have measured the capacitance in a calibrated way, you can extract the dielectric constant. Knowing the thickness of this dielectric film is very important in this measurement. Without this information, it is impossible to draw any quantitative conclusions if you're using this model. But you can also work with the bulk samples, and then the extraction of the dielectric constant requires calibration standards. And if you have these standards, your measurement is more precise than the one that is made with electrostatic force microscopy. This you can see on this figure on the right. Another popular application of SMM is extracting the information about carrier concentration in semiconductors. Here you would apply a bit modified model because now you have two capacitance in series. The first capacitance is the same as before, tip, oxide, and then the interface with the semiconductor. And the other one is the depletion capacitance of the semiconductor. In this case, you measure both of them, but your interest is in the depletion capacitance, from which you can calculate then the dopant density. Again, to use this model, you need to know the thickness of the oxide, and often it is a difficult task. So much that some researchers would wash away the oxide and grow a new one in the controllable way, so they know the exact oxide thickness. Now I would like to briefly say a few words on a very important but often overlooked topic, the topographic crosstalk. Once we start coupling the microwave with the cantilever and the coaxial transmission line is broken, the wave starts radiating its energy into the free space. Because unlike DC currents that stay inside of the conductors and would not have large energy losses, the microwave live and propagate through the free space and a very thin layer on the surface of the conductor. And like a transmitting antenna, the cantilever and the tip would radiate the microwaves into all of the free space. So any topography on the surface would affect the S11 measurement, unless the tip is fully coaxial until the very end. The less topography is on the sample surface, the better is the S11 measurement, and an ideal sample would be a perfectly flat sample. Here, I would like to talk a bit about two different SMM modes of measurement. The basic SMM mode, as we already know it, is the S11 measurement. In this case, the source and the detector are working on the same frequency, a high frequency of several gigahertz. And the spectrum is rather simple. It's just one tone and there is nothing else except this tone. This mode works well on a large range of samples. the dielectrics, semiconductors, semi-metals, but it does suffer from the topography crosstalk. It turns out there is one kind of samples where the applied bias voltage can change the tip sample impedance, and those kind of samples are semiconductor materials. In semiconductors, when you apply a gate voltage, you can populate or deplete the carrier density under the tip. This is a nonlinear effect, and this effect can be used for frequency mixing. So if you apply low frequency bias to the tip or to the sample, this low frequency will mix with the high frequency of the main tone, and this will give rise to the satellites or the sideband peaks in our frequency spectrum. So now we excite the sample with low and the high frequency together, and we detect the product of their mixing, the sum of these frequencies. So the source and the receiver are not working on the same frequency anymore. So this would be so-called DS-DV mode, and it is very close to the DC-DV mode from the scanning capacitance technique. This mode works only for the semiconductors, and it is not affected by the topography as the standard S11 measurement. There could be different technical realizations of this mode. For example, using a mixer and mixing down the product signal back to the DC, and using a lock-in amplifier working on the frequency of the low frequency modulation. But a better way is to set your detector to work directly on the sideband frequency and directly measure the RF signal strength here. This way is preferable because you would be much further away from 1 over F noise. Now let's talk about the limits of the DS-DV mode. What can we realistically measure with it? Here is an example of what a typical calibration curve looks like. If normalized, the dependence of the capacitance versus the dopant density looks like a sigmoid function. It saturates at both ends of the range of densities between the 10 to the 15 and 10 to the 20 atoms per cubic centimeter. The hand-waving explanation to this is rather simple. To have a signal, you need to modulate the dopant density efficiently enough to create the change in the capacitance. At the higher range of the densities, we're dealing with the degenerately doped and almost metallic samples. And you cannot modulate this concentration because all the states are occupied. On the other side of the spectrum are low doping concentrations, where the depletion region becomes large, size of several microns, and again, the change of the carrier concentration is not changing the capacitance a lot, because there aren't that many carriers to start with. So the typical range of measurable densities is between 10 to the 15 and 10 to the 20. By making slower measurements and integrating over longer times, you could stretch this range a bit, but this is it. For the DS-DV measurement, this range is pretty much the limit. Now, if you'd like to measure smaller concentrations, you could use the S11 mode, with which you can even measure dielectrics. So we have seen that there is a lot in common between the SMM and the scanning capacitance. Both techniques are very popular in making measurements on semiconductors. And on this slide, I would like to give a quick review of the scanning capacitance technique. So not surprisingly, the diagram of the measurement for the SCM has many similarities with the SMM. There's the tip, the oxide layer, the semiconductor, and the depletion region. The difference is the way of measuring the capacitance. In SMM, we measure the S11 parameter, which is a reflection coefficient, and then deduce the capacitance. In the SCM, the capacitance between the tip of the sample is a part of the resonant circuit. There are some parameters that need to be adjusted to find the resonance of the system. And then the sensor is working on the linear region of the resonance curve. In the same way, you modulate the depletion capacitance with the AC voltage applied between the tip and the sample, and you use a lock-in technique to detect the changes in the capacitance while scanning. One inconvenience of such a technique is when you're trying to measure a large range of the dopant densities, you may go over the resonance peak and the signal would suddenly change its polarity. The other thing is that the measured signal is not directly related to the carrier density. The dependence is highly nonlinear, and the only way to get the dopant density information is the calibration samples. Also, SCM only works at a single frequency, which is defined by this capacitance sensor, and it doesn't have an equivalent measurement to the S11 mode. So this technique can only measure the DCDV. So that was the ideological difference between the two methods. Now let's look at the difference between them in the table and see some data. On the right side, you can see the two images of a phosphorus doped wire buried under the surface on the silicon matrix, done in the DCDV mode with the SCM and the DSDV mode with SMM. And we can see a clear difference between the two measurements. Because the SCM mode is usually using lower frequency, the motion of the holes under this RF wave results in a more blurred image of the wire. The SMM is working at a higher frequency and the holes just cannot follow the wave, therefore the image of the wire is much sharper. The aluminum contacts, which are not visible in SCM, are clearly resolved in SMM, which highlights yet another advantage of the SMM over the SCM. If we look at the comparison between the two modes in the table, the SMM has several advantages over the SCM. So first, the SMM has two operating modes, the S11 and the DS11DV mode. Both have their advantages and their areas of application. The SCM has only the DCDV mode. In terms of sample preparation, the SMM is more forgiving. The SCM works best with the oxide layer. And operating frequency, SMM has variable operating frequency, the SCM is fixed. There is a signal inversion in SCM which does not happen in SMM. In S11 mode, the SCM could be used for measuring the dielectric constant. The SCM cannot do that. In terms of range of the dopant densities, both techniques are pretty similar in the DSDV or DCDV mode, but the S11 mode in SMM could be used for measurements of lower densities. Overall, the SMM is technologically more advanced than the SCM and is clearly a better measurement technique. Now, let's look at some data that we have measured while preparing for the webinar. A very typical sample to measure with the SMM is, of course, a semiconductor sample with a range of different dopant densities in it. Infineon is manufacturing this kind of samples for their testing needs in production, and one can buy such a sample from them. It is so-called Infineon SCM calibration sample. It has N-type and P-type dopants, both ranging from 10 to the 15 to the 10 to the 20 atoms per cubic centimeter. And it is well characterized by both techniques and multiple publications on the topic. If you're interested, you could start reading with this publication and then look up the references in other articles. In our measurements, you can see a clear contrast between different dopant densities in both amplitude and phase across the whole range of those densities, same as in any other publication on this sample. In the S11 measurement, it is not possible to judge what type of the dopant is on which side of the sample. In the DS11DV, same as in DCDV measurement, the phase information can indicate the type of the carriers, as clearly can be seen on the image in the right bottom corner. This phase difference is coming from the difference in the mobility between the electrons and holes. Here I would like to say that DCDV works well for silicon or germanium, but for the 3,5 semiconductors not so well, because there is always a layer of arsenic below the oxide, and this layer of arsenic is metallic. So the extraction of the information about the dopants from the DCDV in 3,5 semiconductors is difficult. An S11 measurement would work better for 3,5s. Another calibration sample, and also simultaneously a sample that cannot be measured with the SCM, is the MC2 Technologies capacitance standard, which was originally developed at NIST for the SMM measurements. The sample consists of several silicon oxide terraces of different heights on the silicon substrate, with golden dots of different sizes on those terraces. Again, this is a very well studied sample, and there are many publications on it. And one of the recent ones made by the researchers from LNE, and inside you can read about the determination of the capacitances of different golden dots with the SMM, along with the calibration algorithm on how to do that. The same algorithm is widely used now by many researchers and most of the metrology labs which are working with the SMM. And our measurements, you can see a clear contrast between the terraces and the dots. And in fact, these silicon oxide structures are often used to measure the device performance because they are of known thickness, and it's easy to recalculate the thick signal into the change of the capacitance. And from this, you can determine the capacitance noise of the instrument. Let's look at the calibration procedure in detail. It is a very important topic because this is the easiest way of getting quantitative data from the SMM measurement. First, we need to understand that the S11 measured at the input port of the receiver is not the same S11 which is on the interface of the tip and the sample. Between the port and the tip sample interface, there is a transmission line. And the calibration procedure is essentially there to characterize this transmission line. No matter how complex the line is, it can be described with the set of the 4 coefficients. Here we would call them the error coefficients. One of those coefficients we would assume to be equal to 1 because we can always normalize the system by changing the other coefficient. Those arrows here, they indicate the propagation of the microwave. In the microwaves, there is a Mason rule saying that the S11 at the port is a product of those error coefficients and the S11 at the tip sample interface. To find these 3 coefficients, you need to make 3 measurements of the S11 in the places where the impedances are known. From these measurements, we can then deduce the 3 error coefficients, and using them, we can use the reverse calculation and apply it to the whole sample, therefore recalculating the S11 parameter in the physical quantity or impedance. And from this impedance, we can then reconstruct the capacitance and then the material parameters. And while doing that, we can also do a sanity check that, what we measured is at these 3 places is exactly what we then calculated. Let's look at how this works on a real sample. We'll take the MC2 sample with the terraces and the golden dots and we'll calculate the capacitances of them, because then we can compare the results against what's published. Similar to a few slides before, we have 2 capacitances in series here. The capacitance of the oxide layer, which we will approximate with the parallel plate capacitor, and the depletion capacitance of the silicon below. As the area of the top electrode, we will take the area of the dot, not the area of the tip, because the dot is conducting. If we did not have this dot, we would have taken the area of the tip. From the 2 capacitance in series, we can calculate the capacitance below the tip. And from this, the impedance of the tip, and then finally the calculated S11 parameter. So we do this 3 times for 3 different golden dots, and we get a nonlinear system of equations, which is tricky to solve directly. However, there is a trick. If we substitute one of the error parameters by a product of itself and the 2 other ones, the system becomes linear in such a form. And this can be solved numerically with any mathematical package. Then we apply this calibration procedure in reverse order, and from the measured S11, we determine the map of the impedances, and from the impedance map, we calculate the map of the capacitances. And the values of the capacitances which just calculated are in very good agreement with the measurements done by other groups. Same calibration procedure can be done when measuring the dopant density. It would just require one extra step, the calculation of the dopant density from the capacitance. To finalize this formula-rich part of the webinar, I would like to show you how to measure the noise of the S11 measurement. I've said before that the silicon oxide structures are ideal candidates for that because the height of them is well known and can be measured. And also the dielectric constant is well known. So we have the S11 measurement and would like to relate the change in S11 when we scan over the silicon oxide mesa to the change in the capacitance. And the noise in S11 could be then directly translated to the noise in the capacitances. For this calibration, we would make 3 measurements of the S11. One on the substrate, one on the mesa, and one in air above the substrate, but on the same height as the mesa. Then we would use the difference in S11 between air in a substrate and meso in a substrate and build a similar but simpler system, because now we're looking for a linear relationship between the S11 and the capacitance, and we're only interested in the change of it. And it turns out that this step in S11 is equal to the step in the capacitance of 4 attofarad, and the standard deviation on top of the meso is 0.1 attofarad. In this standard deviation, of course, there is also a contribution from the topography, so the real noise of the electronics is even lower than that, and usually is measured on a zero-length scan. To slowly wrap up the demonstration of the applications, I would like to show the measurements of the SRAM sample, which is again a typical SMM sample with different N and P type doped regions in it, which had a strong contrast. This is a sort of a real-life application example, because this would be a working device if it wasn't polished down to bring those structures to the surface. One of the useful applications of the SMM is fault detection, where one would like to see if there is a connection missing, or the opposite, there is a connection where it shouldn't be. And in microelectronics, the SMM is the technique of choice for the fault detection, particularly due to its ability to see below the surface. And the subsurface imaging with the SMM is well documented. Here are just the two examples of such imaging below the surface. One is the phosphorus layer buried below the 15 nanometer of silicon surface, and it has a clear contrast in the S11 parameter. A second experiment is more interesting because there the researchers did sort of a SMM tomography by varying the wavelength. They were probing different depth below the surface, and they were able to obtain different images for different layers as far as 125 nanometer below the surface. This technique is based on skin effect, because the different wavelengths of the high frequency radiation would have different penetration depth inside the material, and these depths are material dependent, while in metals that would be tens of maybe hundreds of nanometers. In semiconductors they would be larger, even up to 1 micron. Here is, for example, a measurement of a metallic wire buried below the surface of silicon, which we believe is about 1 micron deep below the surface, and still is clearly visible. Let's say a few words about the hardware. As we already know, the microwaves are best transmitted through the coaxial cables. Once the coaxial structure is broken, the wave goes everywhere and in the free space, and it's losing its power. So it's very important to bring the coaxial line as close as possible to the cantilever, and therefore you need a special cantilever holder, which we have built for this purpose. Here's how it looks like on our Flex FM. Here you can see the microwave connectors integrated in the cantilever holder, and here's the PCB, which is a coplanar waveguide to bring the 50 ohm as close as possible to the cantilever. The cable is a low-loss coaxial cable, and it interfaces the cantilever holder with the RF electronics. The connection to the electronics is done via the 3.5 mm SMA connector. For the SMM electronics, we have applied the many years of experience working with microwave technology and rethought the concept of the SMM hardware from the point of view of the lowest noise possible and the highest possible flexibility. We decided to use digital signal processing to work with 1 MHz signals without down conversion of them to DC level to avoid 1/f noise. Our RF signal and the low frequency signal are phase synchronous, so you could study the phase effects better. We have a maximum frequency of 6 GHz, and it could be as low as 1 GHz. Because we use digital signal processing, the filtering is already done on the FPGA level and can be adjusted to whatever the scanning speed is for the best signal to noise ratio. Here are all the important parameters of the SMM electronics in one table. We have the power of 8 dBm, the frequency range of 1 to 6 GHz, the noise of DC capacitance is 0.1 attofarad, the control of the electronics is integrated in our software, And the measurement modes are S11 and the DSDV mode, from which you essentially get the DCDV and the DRDV mode. To summarize, the SMM is one of the important electrical modes of IFM. SMM measures conductivities and dielectric constants of the materials. Ab initio calculations are difficult and time-consuming, but quantitative data can be obtained by the calibration on 3 known standards. The SMM is available on all our instruments, the Flex, the Core, and of course our new flagship, the Drive IFM. I thank you for your attention, and now it's time for the questions.
Yeah, well, not immediately. First, I want to thank you, Denis. Can't see you yet. Yeah, there you are. Well, thank you very much for this concise and clear talk on an admittedly non-trivial topic. I have a better understanding of what can be done with all your coax cables and electronic boxes that I see you often tinkering with. And I'm sure the audience was also eager to learn even more. So let's now head for the, as you already said, questions, answers of the webinar. That is, if I can find the pane here. Yes. So I see already there have been a few questions arrived. So let's start with them while the others are coming in. So the question would be here, what is comparison of spatial resolution between SCM and SMM?
Well, we always say that the lateral resolution of the method is only limited by the sharpness of your tip, because it works in the evanescent wave mode. But from practice, I didn't work with the SCM itself, but with while working with the SMM, I think so it's noticeable that the lower frequencies gives you a little bit worse resolution than the higher frequency, because still the wave is probing the volume below the tip. And if you work with semiconductors, so it can penetrate for quite some distance below the surface. And then the lower frequencies penetrate deeper. So because the SCM is working at around 1 gigahertz and the SMM could work at pretty much any other frequency, so our maximum frequency is 6 gigahertz. So then I would say that SMM measurements have better lateral resolution than the SCM. But also, I think there was a slide of the comparison between the two methods. I think it's very clear that SMM has a much better resolution than the SCM.
All right, thank you very much. With that one answer, you have already touched on other questions that are here in the chat that I thought might be good to, bring up here. So that was a question in the subsurface imaging with the SMM. How deep can you see the structures under the surface, and what is the lateral solution? So lateral solution you have been discussing, but what's the depth that you can go under the surface? Yeah, so the depth depends on how many carriers there are, because they essentially screen the microwave, and so the skin effect. Yeah, it's because you have many carriers. So in metals, this skin depth is not very large. It's order of hundreds of nanometers, maybe a few hundreds of nanometers. But in semiconductors, it could go as far as 1 micron. So in dielectrics, probably even further. So the bottom line, the resolution depends on your material, on your sample, and on your frequency. If you have a higher frequency, then your resolution is better. Yeah, okay, cool. So also like 2 questions actually relating to the frequencies that you have been talking about. So one question is here, I assume that you have an impedance matching component, half wave resonator, close to the tip. What is the typical spacing between operational frequencies in your 1 to 6 gigahertz range? I guess around 1 gigahertz. Wait a second, we'll look it up. So there was a slide with resonance peaks. So
it's not one. I mean, it's a continuous spectrum of the working frequencies, but because of the geometry of the transmission line, so we have these resonance peaks, and the spacing between them is order of 100 megahertz here.
Okay. Okay. So also relating to the frequency, like the maximum frequency, your system has a maximum frequency of 6 gigahertz. Are you planning on going to even higher frequencies? And if yes, how much higher?
So in principle, we can double that frequency relatively easy from the engineering effort. Of course, it would cost more. But yeah, the first so we have plans to sort of improve that system further down the road, and then the first step would be to double in the frequency to 12 gigahertz.
Okay, well, that sounds great. Another question here. You mentioned a resolution of 0.12 attofarad. Does the noise on the images, in brackets stripes, of the silicon oxide structures affect this value?
Yes, of course. So when you measure the noise, so the topography, it contributes to your SMM noise, of course. So then ideally, if you, as I said already, if you want to measure noise of the electronics, you have to do zero length scan. So when you don't scan really, you just measure the electrical noise, not the convolution of it. But just for the sake of demonstration, I made a real measurement of topography with SMM signal.
Okay, sounds good. Although I have to be honest, I was slightly distracted now as I see more and more questions are coming in. So you will sit a little bit with us, Denis. So our next question would be, are these characteristics all for all the ranges of frequencies, or is the operation rather optimized for a given frequency? So this, yeah, I think also relates.
So I already mentioned that. So there are these resonances. So you can work within these resonances, and these resonances are every 100 megahertz on a typical waveguide. It depends on the length of the cable, depends on what you put on there, even on the shape of the cable. But yeah, so you can work at any of those frequencies.
Okay, nice. So what is the next question here? Is your hardware compatible with coaxially shielded cantilevers like the ones developed by the Stanford group?
Well, we haven't gotten our hands on the shielded cantilevers, but if they have the standard sizes, then I can imagine it could be compatible.
Okay, good. So here is a question that I can very much actually relate to. Wait, now the window is gone. So the conversion of the SMM signal to the quantitative data seems complicated. Would it be possible to do these calculations in your software?
Not immediately. So we're still working on the first part of the software, and then the follow-up would be of course we have plans to introduce this calibration into the software, but it probably will happen next year.
Yeah, I mean, nice that the hardware all works, and now I'm working on the software. That sounds fine. Yeah, so what else? Another question. You have given sensitivity and noise for C, so I guess the capacity. What is the sensitivity noise for Z values?
Well, it's defined by the AFM, not by the SMM. And you mean sensitivity noise for the impedance? Yeah, you've seen the capacitance part, so that was about 0 to attofarad. We didn't estimate noise on the resistance part. So yeah, and if you mean Z is the topography, then that noise is defined by the FM system. So I think it's 35 picometers.
Okay. So another one. So yeah. So this, I don't know immediately whether I understand that one, but maybe you do. Could your system be used with a tiers part VNA, like VNA?
Right. So the cantilever part or the cantilever holder part, it ends with the connector. So to this connector, you can connect any microwave electronics you want. So you can connect the VNA too. So there's no need necessarily buying our electronics. So that's, if you have your own VNA already, you could use it too.
Okay.
3.5 millimeter connector.
Yeah. Okay, I see. Now I also understand the question and the answer. So that might be also an important question. How much extra do you have to pay for over flex? For flex, if you don't have that option. Yeah.
So I cannot answer that question. So you have to.
Yeah, I was thinking that probably sales might be better.
Sales representative in your country. So it depends on many factors.
Right. Just needed to prevent that I'm sitting in the dark in a moment here. So now I'm back.
The shades are closing.
Yeah, the shades are closing immediately to protect us, our precious faces, from the sun. So, but yeah. What is else there? Can we operate in intermittent contact mode or only contact is a question.
So in the moment we operate in contact mode. However, well, yeah, I don't know if I should say that. So we will have we will be introducing another mode in November. So stay tuned. Look for the webinars in November. So the SMM technique will be also operational with this other mode that we'll show in November. So it's currently it's only contact, but next year, or even like from hopefully January next year, you will be working with this other mode.
Sounds ominous. Sounds interesting. Well, what might it be? Yeah. Next question. So, how much variation do you typically measure when calibrating different tips? In other words, is a calibration measurement essential for every single tip, or can one safely assume that one tip behaves much like another?
So you have to calibrate not the tip, you calibrate the sample. So what I said, there was a slide that microwave is affected, so it radiates a lot. So it's affected by the environment, and it's much affected by the type of the sample you have. These S11 parameters. So if you have a new sample, you have to calibrate for this new sample.
Okay. So another question, and could we introduce measurements at different heights from the surface?
Yes, that we could do if you know where your surface is, so you can just lift to some nanometers above the surface. We have in our software this. You can even do the contour mode, so that we have two. So you can measure first topography and then measure the contour around this above the surface. And you can specify how much higher you would like to go.
Yeah. So I think there's one more question, but this is again relating to the resolution. You kind of already answered that, right? That it is dependent on the tip that you are using, right? So that means I think yeah, that was quite a lot of questions here. So yeah, I think we went through all of them now. So that's nice. So last chance, shoot a question right now, or shoot us a mail later on. So not really last chance in that sense. So yeah, and otherwise what is left for me is to thank you all for that vivid participation, and also thank you, Denis, again for like giving a very nice presentation and answering all the questions that there were like instantaneously. So yeah, thank you very much, and have a good time.
Ciao, everyone.
Ciao.